All right, we're looking at simple harmonic motion created by a spring, and we're just going to kind of talk through the key ideas related to it. So recall that for an ideal spring, the force that that spring exerts is equal to negative k delta x. So this means the restoring force is the spring force. So if you've got an ideal spring, you have this negative k delta x, which is a restoring force. It's the spring force. And so that means, for reasons that I'm going to skim past here, but if you want to talk about them specifically, we can. But the period is going to be equal to 2 pi square root of m over k. And this is if you have something set up like this. You've got a mass on a spring. The period is just 2 pi times the square root of however much mass you have divided by the k. And this kind of makes sense if you think about, well, the exact details of it won't make sense from this, but the overall relationships you can track. So for example, if you've got more mass, it's going to be harder to move this back and forth, and so you'd expect a greater period. That checks out kind of intuitively. More mass, larger period, because it's harder to move it back and forth. If you've got a stiffer spring, meaning a higher K, then that means that spring is kind of stronger. It exerts a stronger force, and it can move things more quickly, so the period should be therefore shorter because it's got more kind of push and pull back and forth. This, just so you can kind of think about it, if period is how long it takes to do one cycle, and frequency is how many cycles per time, we also know from the relationship that 1 over the frequency is equal to the period, that the frequency, therefore, of this is 1 over 2 pi square root k over m, and the same logic applies, right? You're going to expect it to go back and forth more times if it's stiffer, and you're going to expect that it's going to go back and forth fewer times if there's more mass attached to it. And the energy stored in this is nice and easy. We've already talked about it. It's delta U spring, which is just 1/2 k times delta x squared. So you'll notice that, as the spring is most compressed or most stretched, it has the most energy. Likewise, in between that motion, we also have the change in Ke is equal to 1/2 m times delta V squared. So you can kind of, delta V squared. The delta does not get squared. So yeah, you can kind of track the changes here and think about what we already know about springs and kinetic energy. So let's just kind of write out what we expect to see and do some kind of basic rudimentary analysis here. So I'm going to sketch a rough graph of a spring here, what we'd expect to see. So this is going to be the position or the stretching or compressing, so it's delta x. And we'll go 1, 2, 1, 2, 1, 2, 3, 4. 1, 2, 3, 4, 5. So I'm going to start here, and then 1, 2, 3, 4. I just want to make sure it's a nice sine function for you. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 2, 3, 4. And then all the way up here, 1, 2, 3, 4. And back down here, 1, 2, 3, 4. Okay, so now we've got those kind of key points mapped in. You can imagine a sinusoidal function connecting them. It's not the cleanest, but you get the idea. So now our period is this distance right here in the time axis. So this is our period, because it's how long it takes to have one cycle go through. And this right here is our amplitude. It's the maximum displacement that we have. If we had a position or a velocity versus time graph, well, we know that when it's stretched the most, and if we kind of look at the slope here, it's 0. Let's say this maximizes at 2, but I'm just going to go up to 1, 2, 3, 4, there. So we start off and we get more and more negative slope until we eventually get to 0. And we get our fastest right here. So 1, 2, 3, 4. And then 1, 2, 3, 4. So it's nice and diagonals here for me. And for those of you in calculus, or those of you that have taken calculus, it'll be nice and easy to see how, kind of derivatives work here. Those of you that haven't, you don't need to worry about it. We'll talk about kind of the logic here in a second. But we'd expect something that's more or less a sine function here. So now, what I want to highlight, though, is all of these kind of similar points. And I want you to take note of how these match up. So basically, every time that you have the zero on our position or our displacement, that's when we have maximized velocities. And that makes sense when we talk about energy, because if I have 0 displacement, that means none of the energy is in the spring. All of the energy is in kinetic energy. So that's where we get the maximum displacement, because remember, again, this is V. Whenever I'm at the maximum displacement, that's when I have 0 velocity, because all the energy is stored in the spring. And so this is kind of the logic that we want you to be able to reason with. And so basically the speed and the displacement, we say trade-off, if you want. Whenever I have maximum speed, I have minimum displacement. Whenever I have maximum displacement, I have minimum speed. And then just some things to remember. F is equal to negative k delta x. So this is max when max displacement. The kinetic energy is equal to 1/2 m delta v squared, which if we want to just pretend that 0 kinetic energy is when the thing's at rest. This is max when minimum displacement, so when the displacement is 0. And the spring potential energy is 1/2 k delta x squared. And so this is max when max displacement. And then, of course, you also have vice versa. So the force is minimized when the displacement is minimized. The kinetic energy is minimized when the displacement is maximized, and all those trade-offs. Most of the questions will deal with qualitative kind of describing or identifying on a chart where these different values occur. And so that's why I wanted to take a minute to really sketch this out, and give it to you like this. So we'll leave it at that for springs. Pendula, you're going to see are going to be really similar, and we'll jump into those in the next video.